everyone. My name is Arthur Sainio. My colleague here with me is Pekon Gupta. We're from
Hello.
Smart Modular Technologies. Today's presentation is called Scaling NVDIMM-N Architecture for System Acceleration in DDR5 and CXL enabled systems. So let's get started. So why is persistent memory needed? System downtimes are costly, but inevitable. When systems lose power or crash, they need to be rebooted into the same state to minimize disruptions. Persistent memory is critical for saving things like intermediate transaction states, configurations, and metadata, even before the transactions are fully committed. For example, data in flight would be in that category. Persistent memory is critical to help identify the causes of failures because it's used for error logging and also for security logging in the cases of malicious attacks. Persistent memory preserves event logs across power cycles. On the other hand, there's the need for low latency memory. So typically high latency may impact revenue or customer experiences. Missed service level agreements like the denial of transactions in a credit card business could mean losing business or losing to competitors. In high frequency trading, a broker could lose millions if their electronic trading platform is just a few milliseconds slower than the competition. Amazon, for example, found that every 100 milliseconds of latency cost them about 1% in sales. Google also found that an extra half a second in the search engine page generation time dropped traffic by approximately 20%. So there are essentially two main types of persistent memory options in the industry today. On the left-hand side, you have NVDIMM-N. That's volatile memory, DRAM memory with power backup. It offers low latency, typically less than 40 nanoseconds, the same as DRAM. It has granular byte level access, high reliability and unlimited endurance, which is the same as DRAM. It has data retention equivalent to the NAND media that's used on the NVDIMMs, typically in the medium density ranges. The drawback is the backup holdup power that is required for NVDIMMs. And we'll also be talking about the CXL enabled NVDIMMs in the next few slides. And then on the right, you have the non-volatile media-based solution. So typically that's the Intel Optane PM, which is used widely across the industry today. It has slightly higher latency but it also does have high density and granular byte level access. So both of these solutions are used across the industry today. NVDIMMs have a long history of filling the latency gap, as you can see in the table or the chart in the middle of this slide. NVDIMMs originated as an accelerator for cache on battery-backed storage arrays. We had DDR2 NVDIMMs in approximately 2007 and 2008 timeframe. These evolved to DDR3 and then to DDR4 NVDIMMs. Then we had the adoption or the formation of SNIA's NVDIMM persistent memory group, which is still ongoing today. It had a significant impact in creating a lot of collateral and educational material and webcasts on NVDIMMs and how they work. And then also in parallel with that, we had quite a bit of JEDEC NVDIMM standardization activity. All of these helped to bring NVDIMMs to the market and enable the ecosystems. They provide direct access and they remove the I/O for the case of NVDIMMs. They allow critical databases to be stored in memory. They use off-the-shelf components, DRAM and flash, which are typically JEDEC standard. And then they've been widely adopted, typically by flash storage array applications. So a couple of use cases here on the left would be as read caches. This is for NVDIMM-N. The NVDIMMs cache hot data and metadata, thereby enabling high performance with latencies, as we mentioned, the sub 80 nanoseconds. And they're orders of magnitude faster than SSD, so you're increasing your system performance dramatically. Also on the right, for fault tolerant applications, the mirroring data to and from the NVDIMMs via the PCIe non-transparent bridging, and they provided in that case 4x improvement in system performance. The NVDIMMs have a established ecosystem, as we mentioned. So on the top, you have applications that are supported in Linux and Windows. The BIOS and the MRC support NVDIMMs with the I2C command set, and also the JEDEC defined SPD. And then there's many NVDIMM enabled systems in use across the industry today. And then lastly, the NVDIMM system power management on the bottom. So you have to have the power and health monitoring for both the NVDIMM and for the power backup source. This also includes the hardware triggering mechanism, ADR, asynchronous DRAM refresh. The DRAMs need to be put in self-refresh before they're read to. And then you have to have some type of power source to back up the DRAM while the data is being transferred to the flash. And then the NVDIMM Cookbook, for those of you who remember this was widely used. It helped to educate the industry. It was a recipe, if you will, for communicating and educating how NVDIMMs are adopted and used today. We also have on the right the ACPI 6.0 NVDIMM framework. And then lastly, the SNIA NVM programming model to address the ongoing proliferation of non-volatile memory functionality, and also for the new non-volatile memory technologies. So now migrating to DDR5, we have higher bandwidth up to 6400. We have lower power, higher memory efficiency and lower latency, and then specifically higher memory capacity for NVDIMMs, typically up to 64, possibly 128 gigabyte densities, and then similar form factors as with DDR4 today. So RDIMM and LRDIMM form factor and functionality for NVDIMM for DDR5. Okay, so Pekon, if you take it away here on the NVDIMM DDR5 and NVDIMM architecture.
Sure. Thank you, Arthur. Hello, everyone. My name is Pekon Gupta. So as we have heard in this presentation today, is NVDIMM-N kind of an architecture is here to stay. It's just migrating from DDR4 to DDR5. So let's discuss the changes in the architecture and have a deeper dive of why these changes are required in a DDR5 NVDIMM-N kind of an architecture. Let's start with something, the key differences between DDR4 DIMMs and DDR5 DIMMs, which are shown in the table here on the bottom right. The data bus in DDR4 DIMMs is a single channel 72-bit wide bus, whereas in DDR5 DIMMs, it's a dual channel, each channel with 40 bits of data, which is what you see in the picture over here as channel A on the further left and channel B as on the right hand side coming from the host system. The sideband bus is incremented from I2C to I3C, and the speed has increased up to 6.4 Gbps in DDR5 DIMMs. But the biggest differences are on the I voltage. The I voltage for the DRAMs have been decreased from 1.2 volts in DDR4 to 1.1 volt in DDR5. This is very important for NVDIMM-N architecture because at lower voltages, you can supply more current you can sustain longer durations and keep the data alive or transfer the data from DRAM to the NAND flash, which is what the NVDIMM- architecture does during a power loss. The other important aspect is the power management. In DDR4 DIMMs, the power is managed by the host motherboard, but in DDR5 DIMMs, the power is managed on the module. This is where you see the PMIC block, which is inside the module. It's a power management IC which manages the power for DRAMs and any other circuitry on the board. Having an NVDIMM-N architecture or having PMIC on an NVDIMM-N architecture is very helpful because now you have a local control over how the power has to be managed within different components of the system. So what happens for when the power is lost? When the power is lost, a host interface indicates a loss of power through an external sideband signaling, and the non-volatile controller, which is what is shown as a box in the middle of this block diagram, copies the data from the DRAM into the NAND flash. During a power restore operation, while the data from the NAND flash is copied back into the DRAM. During a backup or a restore, the encryption and the decryption of the data is also done by the non-volatile controller, which is shown over here. Arthur, we can move to the next slide. So why is there a need of a persistent memory if we already have DDR4 NVDIMMs and now we have DDR5 NVDIMMs? So as you see, for the current generation of CPUs, the number of cores has increased or almost doubled, but the number of DIMM slots on a CPU socket haven't been keeping up with the same pace. And therefore, there's a need to attach the memory beyond the parallel interface or just the DIMM slots. And this is where some of the new protocols like CXL, OpenCAPI come into play because they attach the memory on the serial interface. This is cache current interfaces, so you would see a similar latency and the performance as you would see on a direct attached DDR4 or DDR5 DIMMs. And hence, the similar architecture, what we see for a persistent memory in NVDIMM-N kind of an implementation has to be replicated for CXL interface. This is what we call as NV-XMMs. So NV-XMMs are equivalent of NVDIMM-N, but on a CXL bus. We'll cover some of the architecture deeper dives of NV-XMM in the next slide. Art, please move to the next slide. Thank you. So let's start with what are the key requirements of a NV-XMM or a CXL-based NVDIMM-N module. The first and the foremost requirement is it should have an onboard power source. The key requirement is that data should be self-managed and the backup power should be self-contained within the module. And this is very important for memory modules which are connected through a serial interface because they can be physically removed from the chassis. The EDSFF form factors can be plugged out or hot plugged back into the chassis by an end user. And therefore, the power source, which is used for backing up the data from DRAM to NAND, should be maintained or should be available on the module itself. The second important aspect is it should be self-managed. Unlike NVDIMM-N, there is no host interface which can trigger a backup option. There can be an in-band signaling where host indicates the data has that the power will be lost, but in an abrupt power or unmanaged power fault, the power fault has to be detected locally by the module. And therefore, it's important to have a circuit on the module itself which can detect brownout conditions, power loss conditions, and power restore conditions. The third and the most important aspect is from a software point of view, the programming model. We do not want to define a new persistent memory CXL programming model. It should reuse the existing CXL type 3 device programming model. A type 3 means a memory expander device which supports both CXL.MEM subprotocol and CXL.IO subprotocol. The few other requirements are it should have equivalent latency and endurance like DRAM. This is actually very critical to all the memory devices, not just the NV-XMMs. For memory use cases, the latency is a key factor for all the memory modules. And this is where the NVDIMM- architecture on CXL becomes very critical because you are writing directly to the DRAM, not to any persistent media, which will cause a latency penalty. Another important aspect is the reliability. Even a single bit flip on a memory module can cause either the whole system to crash, or it can introduce new security loopholes in the system. So you need to have practically unlimited endurance. And this is where the DRAMs as a media are the best fit because they can be infinitely written. The only time when we use a flash is during a backup, which is very infrequent over the lifetime of the whole device. So the NV-XMMs pretty much have unlimited endurance during a large or a longer run time of its lifetime. Last but not the least, the encryption is a very important aspect because when the data is sitting inside the NAND flash, you may want to encrypt it before it's being backed up. The NVDIMM-N, NV-XMMs are available in different form factors. They are available in EDSFF, E1s, E3s, and even add-in cards. Now let's dive deeper into the architecture of NV-XMMs. Thank you, Arthur. So what is difference between the NV-XMM and NVDIMM-N architecture? The key difference, if you see over here, is the CXL type 3 memory buffer. It's actually a CXL controller. Unlike NVDIMMs, the host does not write directly to the DRAMs. It has a serial interface to the CXL memory or CXL memory buffer or CXL controller, which converts the CXL protocol into the DDR protocol and writes it back to the DRAMs. This memory buffer adds a hop and has its own buffers, internal buffers, and its own configuration. So it's very important that before the backup, all these buffers which store data in flight should be flushed to the DRAM. This is a critical difference from a standard NVDIMM-N architecture where data is directly written to the DRAM and there is no hop in between. So if you look at the sequence, the first sequence is the module should be should be able to support power loss detection and should be able to flush all the buffers into the DRAM. This ensures that all the data in flight is clearly written into the DRAM before a backup to the NAND is started. Another important aspect is the CXL type memory buffer or the CXL controller will have its own configurations, which can be user specific or customized. These also should be preserved across the power cycle, and therefore these configurations also need to be backed up in some kind of a NOR flash so they can recover or can be restored easily. Once you have flushed all the data to the DRAM and you have saved all your configuration to the NOR flash, then you follow the standard next step of copying the data from the DRAM to the NAND large pool of NAND flash. This is where your non-volatile controller comes into picture. It copies the data from the DRAM through its own bus and backs it up in the NAND flash. On the restore cycle, the same steps are repeated in a reverse order. I can move to the next slide. So having seen both the types of architecture, a standard NVDIMM-N architecture and an NV-XMM architecture, we can now do the comparison between different types of persistent memory in the CXL world. On the left, you have a NV-XMM architecture, which is NVDIMM-N architecture ported to a CXL interface. On the right hand side, you have a purpose-built CXL controller which supports persistent memories like MRAM, ReRAM, phase change memories, or NRAMs. The key difference, both these architectures support byte level addressing. They do preserve the data across the power cycles. The key differences is in terms of latency. In the left-hand side NV-XMM architecture, since the traffic is running at DRAM speeds, the latency is lowest. We tend to achieve less than 100 nanosecond, and it's possible to achieve less than 80 nanoseconds of round-trip latency on an NV-XMM kind of an architecture. Another important aspect is the reliability. Since the data is written or encrypted and it's only stored on the NAND flash during a power loss cycle, you pretty much have infinite endurance and this gives a better reliability for memory applications. There are some challenges on the XMM side because of the backup power. The density of the backup power and how much current it can provide decides the capacity of the NV-XMM devices. So there are differences between the usage models where NV-XMM is a good fit for number of applications. I'll give the control back to Arthur for summarizing the details.
All right. Thank you, Pekon. All right. Well, thanks. Just to summarize and talk about a few key takeaways here. So first of all, NVDIMM-N architecture is transitioning and scalable from DDR4 to DDR5. We are using the industry ecosystem, all the work that's been done over the many years to utilize NVDIMMs that can be leveraged into DDR5 with providing significant performance benefits for end customers. Latency sensitive data is continually changing and can benefit from NVDIMM-N. DDR5 is here now. NVDIMM-N is in the works and can provide a near-term solution while other industry activities are going on with CXL and others. And then again, on the bottom there, NV-XMM architecture will use similar architecture, both NV-XMM and NVDIMM for low latency sensitive applications. And they will coexist. So NV-XMMs and NVDIMM-N will coexist together and open up, in addition to just caching, and it could open up new applications for higher density, higher capacity, and composability. So thank you so much for taking time to listen to this presentation. We look forward to your comments and questions, and we can hopefully get the answers out back to you. But thank you again for your time, and take care.
Thank you.